tell you a story related to the fractional quantum Hall effect. What I'm going to tell you is very different from what one would learn in normal textbooks or review of the subject. Most of these are not central subjects in quantum Hall physics, but due to I hope these are of interest to people here. You see, they have some. I hope convince you they have some intrinsic beauty in trying to view the quantum Hall system as some kind of a fluid, as I was instructed to do for this lecture. So last time we start our let's start our discussion with the writing down the Hamiltonian for the system. So sum over A k squared over 2m. A is the particle from 1 to A. K, remember, so K is P minus EA. X, which is the last time we called that the kinematic momentum, plus the potential energy sum over all pairs of particles, P of XA minus XB. Basically, this is the theory of everything. And we derive all the consequences from that theory of everything. Okay, so the integer quantum Hall effect last time is the following picture. We have Landau levels of one particle moving in a magnetic field would have its energy organized in Landau levels. Say a simplest quantum Hall effect with n equal to 1 would correspond to the electron filling up all the state in the first Landau level. But now you have now what Stomer and Gold does this in 1910 is they crank up the magnetic field by a factor of 3. So when the magnetic field is increased by a factor of 3, the degeneracy of the a Landau level increases by a factor of 3. And now you suddenly find yourself in a situation in which there is less electrons than the number of states available on the lowest Landau level. So the filling factor here is equal 1/3. And this picture of non-interacting particle will not tell you how you distribute this particle amongst these orbitals. So the problem becomes difficult. It will become not possible to solve without taking into account the interaction. Now, let's discuss the two energy scale in the problem of the fractional quantum Hall effect. So one energy scale is the distance from one Landau level to the next. Let's call that omega c, cyclotron frequency Pb over m. There's a one omega c. And then there is another one that is the Coulomb energy. So the Coulomb energy, Coulomb interaction, potential energy. Okay, so it's E squared divided by the typical distance between two particles. And in the case of the fractional quantum Hall effect, this is roughly E squared over LB, where LB is the magnetic length that we have defined in the previous lecture. BB. It's because the density of electron corresponds to the 1 electron per roughly LB square area. And so you can see here, this Coulomb interaction energy behaves as square root of B. And this one we have like B when we change B. And so if one increase the magnetic field, this energy scale at some point will going to be much larger. So this is the regime that theorists like to be in, because in this is a regime where things are maximally non-trivial. These Landau level presumably give rise to some kind of a set of state. The interaction is going to split the degeneracy, and we have a set of state, but the energy scale here is going to be that energy that we call that delta, which is still small compared to the distance to the next Landau level. So we are going to consider this regime, which is called the lowest Landau level regime. Concentrate our attention on this in this regime. Okay, so any question? Okay, so now what's going to happen in this regime? So let's recall one thing that we've done in the previous lecture. We have introduced the notion of guiding center. Okay, this is a very classical concept. Basically, if you have a particle in a magnetic field, then it moves along a circular orbit, and the center of the circular orbit is located at coordinate r, and we define as x plus 1 over n. Might get the sign wrong, but with me, I think this is c plus k. Could be plus or minus here. Let me just quickly check the sign. I think this is plus. So guiding center is this r, and the property of this guiding center is that it commutes with the momentum k times kj. So I'm going to try to stay in classical physical most of the time. So Watson bracket between r and k is 0, with the consequence that if there is if a particle experience nothing, no external potential except experience only a magnetic field, then it in orbit r is going to commute with the Hamiltonian. A square over 2m is equal to 0. Okay, so here I'm going to use this guiding center coordinates to try to address the problem of many interacting particles. Can we get some insight into the dynamics of a system of n particles? Each of these, so you imagine each of these particles move in a certain circular orbit. Well, it's a very classical picture, of course, but I'm just to make sometimes it's good to have some kind of a picture in our head. So these move, and also they interact with each other. You know that when the particle have a force act on it, this orbit will drift due to the interaction potential with other particles. So problem becomes a collection of these particles simultaneously going through the orbit and then drifting. And then we have to impose on that quantum mechanics. That's how I think about that. Right now, if I'm going to go to that. So this orbit appear because of the k-square term in the Lagrangian. I'm going to make the problem simpler by factoring out this circular motion. The circular motion has frequency that is omega, very fast compared to the energy scale of delta that we are interested in. So we are going to want to average out this very fast cyclotron motion. So averaging out the cyclotron motion means that we are going to do in the Hamiltonian sum over a square plus sum over a and b of x a minus xb. this term we are going to drop. Basically, from the quantum mechanical point of view, all these particles are on the same Landau level, right? So the kinetic energy is the same, k squared is the same, so it doesn't make much difference with the Hamiltonian to drop all of them. Now we have this. Now, last time we said that if the potential is smooth, then we can replace this by sum over A and B of the potential between, we replace the x by the guiding center coordinate. If the distance, typical distance range of the potential is larger than the cyclotron radius, the magnetic length, then it's possible to do. And so we have this Hamiltonian, just the potential energy, but the dynamic is still complicated because the guiding center coordinates do not commute. So if we have two guiding center, Ri and Rj, last time we derived this, I think it's something like minus Lb squared epsilon Ij delta AB. We didn't have delta AB last time because we are talking about the same particle, but here A and B are the indices of the particle. And so we have the coordinates of two different particles commute, two coordinates of the same particle have this commutation relation. So we have basically, one can imagine the problem is a problem of n of these guiding center coordinates living in sort of a phase space, because x and y coordinates do not commute. Basically, we have particles living in the phase space and then interacting with each other with a Hamiltonian pairwise interaction Hamiltonian like this. And classically, the equation of motion for this particle would be given by the Poisson brackets of this R. It's pretty simple problem. Even in the classical level, I don't know whether this has been studied or not, but we know that at the quantum level, the quantum version of this problem gives rise to all the richness of quantum Hall physics can be traced back to this simple model.
Magnitude is fixed. It's just rotating velocity, right? So
at the lowest Landau level, all this
magnitude of k is fixed. It's just the
magnitude of k is fixed by the energy, right? The lowest energy. So the lowest Landau level has the minimal area. And this all is fixed.
So then, R is displaced from x, or x is displaced from R by
k. Yeah. And so here, one thing that I have to say is that this approximation of replacing V of x to V of R works only with the typical distance between this R A minus RB is much larger than the magnetic length. But you can do a more careful quantum mechanical analysis. And the result of that is that the lowest Landau level projection still can be done, but the form of the potential is slightly different. Instead of the original potential V, like Coulomb 1/R, we have a new potential that is V tilde. And the relationship between V tilde and V is very simple. Okay, E2 minus K LB square root 2. The Fourier components of this field tilde turn out to be just related to the Fourier component of original V times a Gaussian function. And that can be done fully quantum mechanical. Okay, so now we have this problem of n particles essentially living in phase space and then moving into field one of the other, and then they do something in field theory. How do we going to treat this problem? So in physics, in theoretical physics, there are typically two ways to address the problem. One can try to understand where all these quantum Hall plateaus appear by trying to solve the problem bottom up. That is the Hamiltonian, try to do approximation. In the case of Laughlin, what he did was to have some kind of jump to guess the wave function and then derive the properties of the system using his wave function. There is also another approach called composite fermion, which is a little bit more constructive. Try to understand, which another way to try to understand how the quantum Hall plateau appears. Another approach sometimes is taken in theoretical physics is to give up understanding microscopically the appearance of the physical phenomenon, assuming that we know something about the nature of the ground state, and try to use symmetry principle, some kind of other principle to derive different relationship between different physical quantities. So this approach is one example where this approach is done in QCD. Quark and gluons interact in a very complicated way with each other. We still don't understand how they give rise to confinement and hadron physics, but there are many features of the hadronic physics, especially interaction between pions, can be understood without thinking too much about how pions appear. We just need to know that the pions are related to a pattern of symmetry breaking. So here I'm going to try to find out some information about quantum Hall effect, but not trying to derive them. I'm going to try to appeal to some symmetry principle, and then, but I'm going to derive them through more indirect means. So that we are going to try to discuss conservation law. So the conservation laws are, of course, in hydrodynamics. Conservation law plays very crucial role. And all the hydrodynamic equations are basically conservation. In a fluid, we have conservation of mass, conservation of moment. In a system, in a magnetic field, we lose conservation of momentum, because if a particle moves in this direction, the Lorentz force is going to curve it, and so it looks like we are down in the symmetry. The question is, can we still find some non-trivial symmetry in the regimes where this cyclotron frequency is averaged over? So let's try to do that. So let's first write down the conservation of charge. So rho is the electric charge density. Basically the charge of electron times the density of the electrons. J is the current, electric current. This is a conservation of charge. Now we're going to try to write the conservation of momentum. We know that the momentum is not conserved, but we know how much it doesn't conserve. So let me write down this equation, the second equation. So first, the momentum density is simply m divided by E times J. Because all particles have the same mass to charge ratio, the momentum density is equal to the charge current up to a constant, which is the mass to charge ratio. Now let me write in index form. I J Pij. So I'm not sure if this is the standard notation for the stress tensor, but in gravity, GR, for example, that's how the stress tensor is denoted. is equal, so this one is not equal to 0, but is equal to the total force acting on a unit volume. The total force here is rho E plus J dot B, J cross B. So let me write. So B is along the Z direction, so IJ run on the X and Y direction. Okay, so that's the conservation law. Now, in the fractional quantum Hall effect, we are interested in the regime where I would claim that this term is negligible compared to this term. It can be dropped. And you can do that by estimating. So this term has a order of magnitude of m omega. Omega is a typical frequency of problem we are interested in, m omega over E. And we know that m omega over E is much less than B because we are interested in frequency, which is much less than the cyclotron frequency. So in the fractional quantum Hall effect, we average over all the very fast motion of order omega. And so this term can be dropped. And we are left with an equation that has no time derivative. Just a clear balance of force. Lorentz force has to be balanced by some kind of stress in this liquid. Okay, so now, so let me let's leave it here.
So this is very similar in geophysics, what we would call geostrophic balance, or the Borealis force is balanced against pressure. And then we might think about fluctuations about that. But we would focus on the conservation laws on conservation of vorticity, which would be like local angular momentum density instead of the linear momentum density. And even in a rotating frame, there would be some this quantity, this absolute vorticity. Is there something analogous here? Because it seems it's already quite close.
Yeah, I'm going to discuss that. Because I'm not very familiar with what's conserved in geophysics. Maybe one of the conservation laws that I'm going to derive has this flavor of the angular momentum. Okay, so here I have this equation. Now I'm can solve the second equation. So let's try to solve this equation and express J in terms of the other quantity. So this algebra is very easy to do. Convince yourself that J of I is equal to the following. J of I would be equal to F1 over B, epsilon ij, and then rho E of J minus dk T jk, I think. Then what I can do is that I can put it back into the first equation. Now, eliminated the current. Current is no longer an independent quantity. Now we have the following thing. But before doing that, let me make a comment here. So from here, you can see one of the equation of the fractional quantum Hall effect, namely this if you have electric field, if everything is homogeneous, then this is 0. And then the current is perpendicular to the direction of the electric field. And that's the nature of the quantum Hall effect. In fact, you can derive from here that the whole conductivity is rho divided by B equal to the filling factor divided by 2 pi in unit of P or H square over H bar. So we get this quantum Hall response function, the transport coefficient from the first term. We want to explore the what happens if the system is slightly inhomogeneous, then the stress to contribute to the equation that I'm going to write down, d rho over dt. So you can write this equation, d rho over dt. Then let me write this one. The term to come from here like this. Vi rho minus 1 over b. So now I may be making one sign wrong here, but I think this is do everything correctly. Equal to 0. And let me write down what is this. Vi is equal to epsilon ij E of j divided by b. So this is the drift velocity. We say that if you have the guiding center coordinate drift with in the direction perpendicular to the gradient potential, so E of I, we're going to mostly think about the situation E is a gradient of some potential. So this have a flavor of a certain hydrodynamic equation, but this V, in contrast to usual hydrodynamics, is not something that you would solve the equation for. It's given to us by the external field. So there is certain limitation in this analogy between a quantum Hall liquid and the usual liquid. The flow of that quantum Hall liquid is completely prescribed. And then there is this contribution to the conservation law of mass, of charge. That's quite interesting. Of course, not everything we are doing very basically elementary algebra. We should not hope to explain everything about quantum Hall effect from here. But one thing that we can explain is the following. Already at this moment, we can explain one thing that took people a few years to obtain after the discovery of the fractional quantum Hall effect. That is the behavior. We are going to derive the behavior of the dynamic structure factor. S to omega in the limit t goes to 0. So that's this thing I think is first known around 1986. Okay, so what is the dynamic structure factor? So by definition, so it's proportional to there's some coefficient sum over all excited state, and so we have system in the ground state 0. So then there is rho minus q and rho q. So this is a Fourier transform of the density operator. Yeah, let me write it and then delta omega minus dn.
Yeah. I'm very interested in J. I naively assumed that since you roll times the velocity.
J. Yeah. So here we have this equation over there. That J is not exactly equal to rho times V. Well, it's J. The current is a more fundamental object, right? This V that we derive, that we wrote here, is basically a notation. So you can derive, you can define your J to be your V to be J divided by rho. Then it would be a more dynamical variable. So the dynamic structure factor in a fractional quantum Halls in a gap state always have the following structure. If I plot that as a function of omega, then it's always 0 at one point because the system has to have a gap. So for a gap state, the ground state is separated from the excited state by a certain energy gap, and so the first contribution that comes always have finite omega. So that's why in a gap state we are interested in finite omega that is larger than the gap. There's no information in the lower regime, in the lower frequency regime. So we have finite omega, but we can ask the question, fixed omega, what is the behavior of the static structure factor as a function of Q when you take Q to 0? S of Q omega, when we take Q to 0, go to what? Yeah, for a fixed omega that is bigger than a gap, for any value of omega, fix any omega that you want, and then try to get this omega Q goes to 0.
So by saying like optical capture or like grow
yeah, so this is a quantum version. Yeah, you can also write the classical version, but I'm going to for this question I'm considering the fully quantum problem. Imagine that I've quantized this theory, and then I want to understand it. So we operate the rho here. So this operator rho, basically this operator rho is like rho of x is sum over all particle delta function of x minus Ra. Roughly speaking, this is our operator. And of course, yeah, operator, so this is an operator. Yeah, I'm going to fix omega and then ask what is the behavior as the function Q goes to 0. Now, how did this problem appear in the literature? It appeared in a certain context in the paper by Gerwin, McDonald, and Platzman, when they were trying to generalize Feynman theory of superfluidity to quantum Hall effect. If you are familiar with Feynman theory, this operator of the density acting on the vacuum, acting on a ground state, is what Feynman uses as a trial wave function for a phonon state. So this is quantity that appears naturally in this variational treatment of the excitation. Okay, so and then but we can understand this from the behavior of the static structure factor from the equations that we wrote down here. So here we turn off the electric field. So the equation basically have the conservation equation basically have the form of d rho over dt and then minus 1 over b epsilon ik dj dk di dk djk is equal to 0. Roughly speaking, a first time derivative of omega or omega of rho, omega time rho is equal to some second derivative of the stress tensor. So in suppressing all the indices, what I get is basically q squared times t. I can restore the indices I want, but it will not change what I'm going to derive, which is omega rho. Basically, the operator can be written as q squared over omega times some stress tensor, or then each of these will be proportional to q squared, because rho is q squared and omega is fixed. So this has to be q24. This is behavior that is different from usual behavior of density of the of the dynamic structure function. For example, in a liquid, in a superfluid helium, for example, this would be have like Q square in a usual liquid in the regime of fixed omega. And it also can be understood in a similar way. In the usual liquid, the conservation law is an equation where we have first time derivative and first spatial derivative. And so rho is equal then Q time divided by omega times J. So rho is rho Q, and then this is about the Q square. But in the quantum Hall liquid, the behavior of this function is Q to the 4. If Leo? Non-singular. Yeah, it's non-singular. A small q. So if the system is a gap system with no spontaneous symmetry breaking, then correlation function shouldn't be singular at all, finite q. The reason why I have some 1 over q square, for example, correlation function, where is typically Goldstone boson. Give you that, but if we have a structureless symmetric liquid, nothing seems spontaneously symmetry broken, then TT can
Maybe the long way.
if I have time, I can show that it will not vanish in the limit in some known state. For example, one can show that it cannot vanish for roughly in 1/3 state. The reason, let me give you the reason. It's actually what at the end I want to derive is a relationship between the whole viscosity of a liquid and some topological properties. So the whole viscosity is determine one of the components in the stress correlation function has to be non-zero. So some part of that has to be non-zero.
The other question is, can you, so like when we think of an ordinary fluid, viscous fluid, that's the TIJ, the stress is proportional to velocity, or in proportion to pressure. Like, what is it? What's the structure?
So it depends. So you on the type. So if you have some kind of effective field theory for quantum Hall fluid, then TIJ would be expressed in terms of some effective degrees of freedom. One example is in the theory of composite fermion. So this TIJ would be expressed in terms of derivative of this composite fermion field. In principle, can be written down.
But it's some kind of anisotropic pressure.
Yeah. So if you have some kind of excited state, then when this state this something move in the system, hopefully I can draw some picture. Then there is a stress that goes with it.
So that's a proportion to. It's also derivative of velocity, but not dissipated. Rotated.
Well, here we are not doing consecutive relation or hydrodynamics in the sense of, so when you try to if you want to express T in terms of P, right, you are basically asking the following questions. Let's take the system and then impose on it a certain velocity by the electric field, and then ask in the ground, roughly speaking, ground state of that system, what is the stress? And the stress turn out to be proportional to derivative of this E. So there is a relationship, some formula that say EIJ is DI EJ plus EJ DI plus dot.
Right.
Yeah.
I guess the point I'm making that it's somehow it's perpendicular, so it shouldn't just it has to come in as some kind of a non-dissipated viscosity rather than, normally if it's a strain, a velocity strain, then it gives you dissipation. But here has to come in, still derivatives of velocity, but somehow 90-degree rotated, so
It's a whole viscosity.
it's a whole viscosity.
Yeah.
So it doesn't just, that's the structure.
It's a structure of some part of this. So this equation is very general. Doesn't assume hydrodynamics approximation, etc. Yeah, this state M can be an arbitrary state. Doesn't have to be close to equilibrium.
Great. When you're doing this estimate, why did we drop the VI partial I term?
So when we define the dynamic structure factor, there's all these states that are living in zero electric field. Right? We have a quantum Hall state in finite magnetic field, and that's why we can draw it.
So
Electric field.
The density gradient is zero.
That's what.
So that means the density gradient is zero because there's no electric field, or
Here in this state, in the ground state, they are zero.
oh,
There's no gradient, but all the excited state can be very different. And we have the static structure, the dynamic structure factor measures the correlation between the fluctuation, quantum fluctuation of density at different points in space and time.
so in the like the equation above, that equation of motion above on the top word, you have the VI partial I rho, and you're saying that then why I'm still confused why we're dropping that term. when we're trying to
Because
calculate.
V is equal to zero. Not because derivative of rho is
E
equal
is
to V is equal to zero, because V is electric field.
And for hydrodynamics, we're thinking
We are not doing traditional finite temperature hydrodynamics here. We are looking at fluctuation, correlation of fluctuation of density in a quantum state. The equation that I wrote down has some hydrodynamics flavor in it. And maybe it fits in this school, but
Maybe we should let you explain the importance of Q to the fourth. I'm still waiting.
why Q to the fourth?
Well,
is
no,
important?
it's just, why is that special?
Well, it's first of all, it's different from the usual fluid, Q squared. And what is different, I probably won't be able to explain, but in this paper, this work by Gerwin, McDonald, and Platzman, the fact that it's Q to the fourth allows them to derive the spectrum of so-called magnetoroton. So I probably won't be able to explain. Namely, there is a formula, there is a quantum Hall version of the so-called Feynman. How do I say? Value formula. The variational, this variational curve goes to a constant only if this S is equal to Q to the fourth. This formula for this displacement curve looks something like omega equal to some numerator divided by S of Q in the denominator. Well, S of Q is an integrated version. So so you can define the static structure factor is the integral of omega S to omega, and it also has to, you have like Q to the fourth. If at each value of omega, you have like Q to the fourth, and if the integral is sufficiently well behaved, then this is also Q to the fourth. And that's what they use to argue that the gap at zero momentum is finite. Feynman, yeah, Feynman doesn't do two fluid. Two fluid model is Landau, Tisa, Kalatnikov. Feynman, what I mean is maybe he did various things, but one of the things he did was to try to explain tone in the spectrum of excitation of helium So Feynman derived a formula that says in some variational ansatz, this curve is equal to basically k squared. Forget how k squared actually divided by s of k. S is the static structure factor. And in helium, we know that the static structure factor has a peak because it's close to solidification. And so this peak in static structure factor explains the dip in the phonon dispersion relation.
But it vanishes linearly with K, right?
Yeah, it's vanished linearly because of the following, because in superfluid, this integral is not actually stretched all the way to 0. So there is some singularity as omega goes to 0 as well. So it cancels one power of omega cancel. Yeah, because of that. Yeah, it's like, yeah. But in the quantum Hall case, because there is no gap, there's a gap, then this integral is very well where we have, and we still get q to the 4 for the static structure factor. We don't do in hydrodynamics actually a two-step process. First, we write down the equation of conservation law, and then we have to postulate some constitutive relation. Say the stress tensor is equal derivative of the velocity. So that step I didn't do here. All I did was to use the equation of conservation. So the only thing that we have here are conservation law. Yeah. So the equations are just conservation law.
Perhaps you can comment on what the dynamic structure factor means experimentally, or like what does the q to the 4, the fact that the magnetorotate doesn't it has a fixed value. What is that? How do you see that experimentally? What does that mean?
Experimentally, this one is not directly measured. We have to have a probe that probe the density of electrons. So usually in solid state physics, that would be neutron scattering. But here actually the experiment, but I think it's not conveniently measured. It's more of things that theorists are concerned about, other than experimentalists and numerical people who do numerical simulation are concerned about this. So why theorists were concerned about this? So there are, as I mentioned in the beginning of the lecture, there are a lot of microscopic approaches to quantum Hall effects. Some of them you probably heard about this flux attachment procedure, etc. Composite fermions. A lot of them fail to reproduce q to the 4. If you don't do things correctly, you get q squared. So that's like a goal that theorists put for their theory for some time, to have q to the 4th instead of q squared. Okay, so now we have this conservation law, which has interesting consequences. But I want to ask the following question. Usually in physics, conservation laws are signals of symmetry. The noise theorem is the theorem that relates symmetry with the conservation law. And one can ask whether there is a symmetry that underlies this strange looking conservation law that has first order in time, second order in space derivative. Is that symmetry? So let's recall how the Noether theorem works. So here it's a little bit a field theory. So I want to give a bit of overview of what is known in field theory. It doesn't have to be quantum field theory, it's just a classical field theory is sufficient. So in field theory, if we sometimes we have a symmetry. So for example, one typical one simple symmetry is the symmetry of a complex scalar field. Perhaps complex scalar field with some Lagrangian that, let me just write down here, isn't very important how it looks like, but say this Lagrangian. It's invariant under rotation of phase of phi, and also tell us that the conservation of charge is related to this symmetry. How does it do? How one can derive this? So one way to derive this is to promote the theory to the symmetry to a gauge symmetry. Make this into a gauge symmetry by including into the Lagrangian gauge field. So let me just write down what usually you would see in beginning chapters of field theory course. This Lagrangian now is invariant under a gauge symmetry, which means phi goes to phi e to alpha x. Alpha doesn't have to be a constant, and a mu goes to a mu plus b mu alpha. So we are not going to treat our a mu as dynamical field. Let's think about this as some background or something that we just put in by hand to the Lagrangian. Fixed, doesn't have any dynamics. Something that we turn on by turning on some external apparatus to create that. But theoretically, it's a device to exhibit the symmetry and the conservation law. Now, this allows us to do the following, make the following statement. Because the theory is symmetric, the partition function of the theory is the integral over all field configuration. So here I renege on my my commitment not to use quantum field theory. Here it's quantum field theory, but very simple. Just imagine that we can take this integral. This integral, because A is not a dynamical field, this integral is a function of a mu, functional of external field. And this is invariant under gauge transformation, because if I make a transformation on A, I can compensate that by changing variable in phi. And if there is, in this case, there is no Jacobian in this change of variable, then this is equal to that. Yeah. In physical terms, nothing depends on the choice of gauge. Things can be only depends on the strength of electromagnetic field, but not by the choice of the potential. But that allows us to derive Noether conservation law in a very simple way. We say that let's expand this z, and rather let me write logarithm of z. Expand this logarithm, assuming that is small. So first order, it is log p of a mu plus integral over dx e over e a mu log z times d mu alpha. That is 0. Because this one and this one cancel. What is written here is 0. For any choice of alpha. And that can be valid only if a current is conserved, and that we can do by integrating by part. E mu, E log z, and E a mu alpha is equal to 0 for all alpha, that means this thing has to be 0. This has to be 0. So this is a quick way to see the connection between gauge invariance and conservation of current. If there is a gauge transformation, then it generates a conserved current. Basically, the conserved current that conserved is the derivative of the logarithm of a partition function in terms of A. And then this tells us that the mu general is equal to 0.
The transmission on phi, you integrate over phi, so it doesn't.
Yeah, we integrate over phi. So if I do this, the mu here, I can say my phi is equal to phi prime plus the mu plus e to the I alpha, right? And then change the variable to phi. And then this trivial. Yeah. So this proof relies on the fact that the measure of integration doesn't depend on the choice of on the gauge transformation. Yeah, so in quantum field theory, there is a whole chapter of anomaly, how this can be violated. But we are not concerned about this here. We just say there's the symmetry. If we have basically the idea is the following. We have a system. Then we turn on some probe, that this A mu can be thought of some probe field. And this probe field, if we can turn it on in a way that respects certain gauge symmetry, so that would give us the conservation law.
I want to make a comment. I'm not huge to the fourth again. I mean, I think that's a general phenomenon of anything in the magnetic field. You know, the strong magnetic field. If you, for example, big crystal magnetic field can be crystal. It's the thing that gives you omega versus q squared rather than q dispersion. I think it's a thing.
Yeah, and I'm not sure if
You know, when you have
I'm not sure if you integrate the thing. Yeah, the proof goes through, but then there is no gap. And so when
no, I don't mean for the structure function. I just mean the fact that dispersions become much softer. You know,
this is not dispersion. This is structure factor.
It's the fact that omega, the rho dot, is proportional to something that has more Q's than you would expect.
That is it doesn't require any quantum Hall stuff. It's just magnetic take care of that. Yeah, I agree. Okay, so this is a very well-known story, but the equations, the conservation laws that we have here are much more much less known. So I want to understand, is there any way to fit the conservation laws that we just have there under the rubric of symmetry? And that turned out to be possible. And it's the topics of our discussion of the higher rank symmetry. Maybe I'm running a bit. Look at my note, maybe before going there, I'm going to tell you why the symmetry. I'm going to tell you why the symmetry is even stranger than the usual. This conservation law is stranger than what we usually used to. So let's again assume there is no electric field, then this zero, the equation of motion, the conservation law that we derive every spot. Now, you can show that the total charge is conserved from this equation, because if I take derivative, Q dot integral dx rho dot. Rho dot can be replaced by this. So it's something that has two derivatives. So it's a full derivative. It's a total derivative. It's actually total derivative of a total derivative. We have even more than it's zero, even more zero. But that's important because if I define the following quantity that has the name, the dipole moment, p integral of x times rho, this is also conserved because its derivative is 1x, and then we have two derivatives of t. And imagine that you do integration by part. You integrate once, derivative acting on x give 1. Integrate twice, you get 0. So this conservation, you have a conservation not only of charge, but also conservation of dipole moment. And moreover, there is another conservation. One can write down x squared. So this is one required a bit of calculation, but as a homework exercise, you can convince yourself that the derivative of that quantity, I don't know how. Let's call that I. Looks like a moment of inertia, so I call this I. I dot is so equal roughly. You find that after integrating by part, is you get derivative acting twice on this x squared. So you get a constant, but it turns out that this constant is epsilon ij times tij, and the stress tensor is symmetric, and so this is zero. So it looks like this derivation is similar to derivation of the conservation of angular momentum. This quantity is also constant. Okay, so what is this? What does it mean in the physical context? This means the following. It means that the charge, first of all, charge cannot disappear. That's real. But if we have a dipole, a plus charge and a minus charge, that dipole cannot disappear by annihilate. These two charges cannot just come together and annihilate. That would violate this conservation law. In fact, this distance between these two objects, if you form it, has to be fixed. It can move around, but the distance between them is fixed. And now there is a third one, this one. This one turned out to do a bit of exercise with the algebra. Convince yourself that once you create this state, in order for this I to be conserved, it can move only in one dimension, in the direction perpendicular to the dipole moment. Can't move up or down. Can move diagonal. Can only move this direction. So this is the symmetry in the system of particle in a magnetic field is quite give rise to quite interesting conservation law. So the requirement here, first, we are have to be on at energies much lower than the cyclotron frequency. So in the fractional quantum Hall effect, that is the lowest Landau level. Again, this is things that it took people a long time to realize that in fractional quantum Hall effect, the excitation, the so-called composite fermion, are objects that looks like this dipole. The momentum of the composite fermion is always perpendicular to the dipole moment. And this dipole moment cannot change. Only when you scatter two of these objects, you can change dipole moment. With the total dipole moment.
Does that mean that the fractional quantum Hall effect realizes dropons, or is this different?
So it is the type of symmetry that appears in papers, most notably by Pretko, and he was trying to write down field theory that captures some. The way I understand it is that these are field theory motivated by fracton physics, and some fractonic models are even stranger than this. So this is depending on what you call fracton. This can be called in a loose sense of fractonic physics. Yeah, so this global conservation, we want to ask what is the field, what is the gauge symmetry that underlying these strange conservation law, conservation of charge. So in this usual situation, there is only one thing that conserves, that is the charge, conserved, and is the U1 gauge symmetry. What is the gauge symmetry story of a fraction of quantum Hall effect with all this conservation law?
What gives that direction? What gives the dipole structure, the plus and minus structure?
Microscopically. So it is the work of Nick Reed. It doesn't appear in straightforward flux attachment. In flux attachment, people have a picture of an electron and then a flux attached to it. And now, around maybe late 1980s, Nick Reed argued that this picture is incomplete. This flux has to be thought of as some kind of a hole next to the electron, but not exactly at the position of the electron. And the distance between this electron charge and this hole has to grow as the momentum of this.
That's the plus and minus.
Yeah, that's the plus and minus. The electron, and then something. I don't believe this picture, to be honest. I believe the situation is even stranger than that. But this picture is very intuitive.
But in the
Jane.
So there is really a point by these really doing the gauge structure.
Yeah.
So there it's attached right to the
And it doesn't have this feature.
Doesn't have-
Yeah. So the straightforward composite fermion theory or field theory realization, for example, Halperin-Lewin theory doesn't have this feature. So it has to be something that you add on top of it.
But what is it? I guess I'm asking, like, what phenomenology, quantum Hall phenomenology, that suggests that it does have the dipole social?
Yeah, that I'm hesitate to answer. I can tell you that I have to think about. Yeah, the phenomenology, there is only few things that that one can measure. So this is not one of the things that is straightforward, as I understand.
But in your theory,
The theory has,
you don't see a dipole?
I not that I don't see a dipole, I put in the dipole.
No, not here, in your Fermi.
Yeah, I have to
There's
put
a
in as an
dipole there.
extra. You have to put it. We have to put it in as an extra, extra term in the Lagrange. Yeah. Okay, so now the motivators to search for a way to understand the symmetry. So, lacking a word, I'm going to call that an exotic symmetry as a result of exotic conservation law as a result of a symmetry. Okay, so we do following thing. So here, how does the current appear? We say that the current is like logarithm of the partition function as a function of A. But think about that as saying in the expansion over A, logarithm of Z of A mu looks like logarithm of Z of 0 plus A mu times J mu. Of course, all that has to be integrated over X. But the derivative with respect to A is J, and so there is a coupling between A and J. So in quantum theory, this log Z, in the classical theory, this log Z becomes just some action. The action at zero field, the action at finite field is equal to the action at zero field plus A times J. We'll try to replicate that in our approach, but now there is only rho and T. Right? So if I'm going to make a guess that we can couple the theory, our theory, by including into the action some term that looks like, let me write this like integral of X rho phi of X times rho of X plus, let me write even more pedantically with 1/2 Hij Tij. So the derivative of this S function of A, derivative of S with respect to phi is our density. Derivative of S with respect to Hij is the Tij. Like derivative of S with respect to A mu is J mu. Any question? So I'm just turning on this probe field. These are probe field, but they have very they are quite physical. The thing that multiply to the density, of course, should be the scalar potential. So that's why I call that phi. And the thing that multiply the stress tensor should be the metric. That's why I call Hij. Should be Hij is the deviation of the metric from the flat metric. So I found some small background metric, perturb metric, and that that metric is coupled to stress tensor. So what condition on the invariant of S that would induce the conservation law? So here, the condition that induces the conservation law is that Z doesn't change when I replace A by A plus D mu A. So one can, having this as a equation as a guide, we can using a method of trial and error derive the required symmetry. So it should turn out to be something like this. Dot means derivative with respect to time. Hij. So here I'm writing down something like LB square k dj dk lambda plus epsilon qk di dk lambda. So if this action is invariant under these transformations on the probe field, then we can rederive the conservation law. The way to do that, of course, is to expand the second expression to linear order in alpha, and then do integration by part as we did in the previous case. So I'm just showing you here schematically. This is ES over the phi is rho lambda dot plus basically T two derivative of lambda is equal to 0, and then do integration by part, and then you get that equation. Yeah. These are any, it doesn't have to be low energy. Any, yeah, so I'm saying that if in the real system, if I put in the probe that coupled to rho, this rho and T, they are real physical quantities that doesn't have to be low energy. So it should be an exact symmetry of a problem on the lowest Landau level. Low compared to the cyclotron frequency. Yeah, sorry. Yes, it has to be, everything has to be low energy compared to the cyclotron.
So like, if you're like a systematic with gases from or field theory goes up.
A field theory. I'm going to try to argue that this appeared in the dynamics of guiding center. That's what I'm going to say. This symmetry that here we are somewhat reverse engineer from the equation from the conservation law actually turn out to be the symmetry of the problem of interacting of guiding centers that move and interact with each other. And it all can be seen even at the classical level. So that
Yes. Those conservation law, those continuity equations,
was derived
you can
from
derive it from Poisson bracket and some assumptions about the structure of the Hamiltonian.
Yeah.
In terms of the,
Yeah, you can derive that. Yeah, and then
so
what?
that Hamiltonian has to have this.
Yeah, and but we can do better than that. We can couple this Hamiltonian to probe this field metric and then the scalar field in a way that is good symmetry. So, yeah, so that's going to be later. But here I'm what we are seeing here is the following: that the problem has to have a certain higher rank symmetry. So the terminology I think is already used in the literature of practonic literature, where the symmetry we have a set of we have a gauge field which combined phi with the metric, and the metric transformed like this. This, but I'm going to write it in a different way. Binding psi I or LD square epsilon I J lambda. To check that this is actually what. But this looks much nicer because this is how the metric transform under small infinitesimal small transformation. Basically, here we have a situation in which we have a symmetry that is a hybrid of the usual U1 symmetry of electrodynamics. So this is like it looks like a zero component of some electromagnetic field, it's lambda dot. But there is no AI component. Instead, there is a metric tensor that transforms as if the coordinate is shifted. Xi goes to Xi plus psi I. That's how the metric transform under this coordinate transformation. So the coordinate transformation here turn out to be area preserving. area preserving diffeomorphism. So in terms of Ci, this is mean Ei psi I equal to 0. So we take a coordinate and then move it around, but the divergence of that displacement is 0. So all the volume is preserved. So we take, say, a certain system of coordinates, and then this move to another system of coordinates, x prime. Trying to draw something, and then x prime is equal to x plus c. In a way that the angle are not preserved, lengths are not preserved, but the area is preserved. Area preserving diffeomorphism.
This is the way by the continuity equation have an epsilon symbol.
The continuity equation,
By having the epsilon symbol.
yeah, it traces back all the way here to this epsilon tensor here, and then it becomes the epsilon in the gauge transformation, and it becomes this. So it's a symmetry that we see here. So now,
And in fact, anything high range these are, well, let's say vector charge, that's the HPC,
no, it has a, it's actually equivalent to one of the theories that Bredko.
one of the
Yeah, one of the theories Bredko is the so-called yeah. Yeah, yes. The traceless, traceless theory. In the so Bredko, there is a he doesn't use this. He used another A. This one is in A0. And there is an Aij, which is a rotating version of this Aij. So if you rewrite all this formula using this thing, this Aij turn out to transform like Aij plus Ei Ej lambda minus trace. Yeah, this epsilon tensor cancel when you go from H to H. So it's one of the theories that Bredko considered. Okay, any question?
So,
Yes.
There's this group of area preserving diffeomorphism with infinite different. You only wrote down a few conserved quantities. Is there a whole hierarchy of conserved quantities?
Yeah, no, it's a similar thing that happened here. So here we have gauge symmetry. It's infinite dimensional, but there is only one conserved current.
Okay.
Because there is only the global part of that gauge symmetry correspond to a conserved current, not the gauge or the gauge symmetry. So similar situation.
So it's different than that incompressible classical fluid. Also this area preserved. So that's an infinite number. Like all the moments of. What's the essential difference between the two? Why?
I think in the fluid, that symmetry is like a relabeling symmetry. So
Yeah.
it's not a
I see, there's no.
yeah, it's not like
There it comes from the dynamics. The vorticity is basically driving itself, right?
Right.
I don't think that's happening.
Right, because the V
His
is
V is
slave.
something slave to electric field.
You don't have an adaptive derivative. In the first.
yeah.
It does,
This
because V
this one is
not-
just
not related.
not related to any dynamic degree of freedom in the theory. So I have very little time left. I'm going to just give you the brief description of what we are going to do next. We're going to try to relate this symmetry to the symmetry of theory that have been written down. Simple Hamiltonian, that is the sum of the potential energy and the difference between the distance between the coordinates, and the theory also has to be completed by the Poisson brackets. Square epsilon I grade delta AB. Can ask whether this theory can be coupled to a probe field in such a way that the whole dynamics is resolved. Now this is completely a classical, basically a classical mechanics problem, and we will see that it's possible. And next time we're going to turn on a metric, basically let this particle move in a space that has a non-trivial metric, and it turn on also phi scalar potential, and we'll show that this symmetry can be traced to this symmetry now can be traced to basically this gauge symmetry is the symmetry of canonical transformation. In R space. So this R space is endowed with the Poisson bracket, so X and P, like X and P. And in X and P space, we can define the canonical transformation. The group of canonical transformation in R space coincide. See how it will. It transforms Rx and Ry, but then in a canonical transformation, the distance between Rx and Ry got shifted. So you have to compensate that by turning on a metric couple the system to a metric, and let the metric also transform under canonical transformation. That is how the metric transforms the canonical transformation. And then the next thing is that this canonical, if the canonical transformation depends on time, you have to also compensate that by letting the system couple to scalar potential with the scalar potential transform. So this starts to be our next lecture.
I have an equation, so we modify the metric based on delta j. Does that mean we're looking at perfect spaces?
Yeah.
So this is quantum gravity. And going from there.
There's no quantum gravity. The gravity is not quantized. The gravity is basically a background thing. So actually, you can imagine a situation that can be done experimentally. You have to distort the lattice so that the mass tensor is anisotropic, and that can be done with laser light, basically in Raman scattering. Some part of that can be done.
In your transformation, why is the lambda has a derivative while the Hij has no time derivative?
Why Hij has no time derivative?
Yeah.
Because we don't need it, right? The way that I've written it down here is that I want to at the end get the conservation law.
Rho dot.
There's a rho dot. So this thing, if it's 0, it gives rho dot plus second derivative of t is equal to 0. So only phi need to have a lambda dot in its transformation. Yeah.
Another question. This is relevant more to one of your slides where you talked about the conservation of the dipole moment, and you talked very briefly about the positive. You had a negative and a positive. Assuming the negative is an electron, what's the positively charged protonic wave?
So again, this is a picture. So it may not correspond to what's happening in reality because it's a nice picture. So in the flux attachment, people say that we attach a flux to the system, but the flux in Nick Reed's picture is associated with the dip in the density. In some in the wave function somehow, the position of that correspond to a zero of the wave function. So there is a little dip in the total density. So it's positive charge and here negative charge. This is a composite fermion theory, so it's not a later.
That's follow up on this question. I mean, so here we don't have any quantum, there's no thought that we're just, I thought we're talking about electron fluid. But charge
And there is must be a
corresponding dip of charge.
Yeah.
That plus minus charge configuration can't relax
right.
by annihilating, and it has to move perpendicular to that distance. Right?
Yeah, if you think about that in that picture, that's clear, right? It's what
Just the guidance
it-
of the
it-
dynamics.
if you have a positive charge here, negative charge here, they usually try to annihilate. There is a Coulomb force attracting them, but because we are in the magnetic field, the motion is perpendicular to the force, and then both of them would move this
Right, that's what I'm
direction.
saying, just guiding.
It's a guiding center dynamic. Derived through some
You're right.
kind of.
We know this dynamics, but you're reformulating in terms of conservation laws.
Yeah, I think there is something we gain here because that give us a certain give me a certainty that it is true. This picture that we have in mind is not something that can be modified by some unknown processes that we didn't take into account. Once this conservation law is just fixed.
How do you get
I can't get this picture. So I said in the beginning, we are not going to try to explain fractional quantum Hall effect, but we are going to assume fractional quantum Hall effect. For example, assuming a gap in this, and then try to get some information. There's nothing about difference between 1 second, 1/2, and 1/3. Yeah, or square root of 3. Nothing.
No, but there's no quantum Hall here at all. I mean, you're really just considering
Particle
magnetic field, electron moving high.
and the dynamics.
That's the only,
Mhm.
that's the only reason, there's no quantum.
Yeah, except-
the Turing factor of 1/3 doesn't really matter.
There's nothing here that fixed
It's just
something
motivating.
special about 1/5, 1/5, 1/3, or 2/5, or 1/2 for that
Say
reason.
that all of these fractional quantum Hall states have this kind of structure.
Yeah, it has to have the structure built in. All this has to be built in, and some of this, as maybe I won't have enough time to explain, but from this symmetry, one can get exact relation. For example, the whole between whole viscosity and the so-called the shift of the quantum Hall state also come from this
There's
symmetry.
certain macroscopic fluidity. Very gentle.
Where's the Hall?
It's in the response to the perturbation of the metric. So here you see that the response of the system to the metric perturbation is tied to response to phi. So that I can tell you one. It's actually I can find out on a formula in Predko's paper that establishes that relationship.
You said that this applies to all quantum Hall states, but didn't you make an assumption that there's a gap? So like it would not apply to like a half full band level?
It would still apply if we say that we fix omega, and then look at the behavior of this function as a function of q, then it will be q to the fourth.
The half full band level, for example.
Yeah.
So
This would still be valid. The statement that Q f is when we integrate over omega. This thing is the static structure factor goes q to the fourth, require that this integral is doesn't have any singularity. When the system is gapless, the q goes to 0 and omega goes to 0 limit cannot be interchanged. And so that's why it becomes not q to the fourth.
I just want to make a comment though in response to Louis' question, which is, Laughlin historically, you wrote down the potential between the guiding centers, and Laughlin considered the plasma of that, showed, the electrons would be separated, and then that inspired him to write down the wave function with the z to the the third power. So there was a kind of connection to the u equals 1/3 system that you could make from this classical. I mean, it's a kind of hand wavy, but apparently he was inspired that way.
I'm not completely sure. I'm not completely sure he was inspired of the picture of the no plasma clearly, but the picture of guiding center. I think the guiding center, if he knew about guiding center, maybe he would not write down, because it from that point of view of guiding center, things are much more complicated.
But he had a plan.
Of the original coordinates of the particle, not the guiding center coordinates. It's purely an initial position of the original particle.
Thank you.